On this episode of MatHAMMatics, we're going to take a look at simplifying radicals. As promised, on this episode of MatHAMMatics, we are going to be looking at simplifying radicals, right? The idea of breaking down a number that is under a square root into its simplest form. So one of the things that's going to be really helpful for us as we begin to think about simplifying radicals is even explore what our perfect squares are, right? And that should make sense here in a second. So take a minute and let's fill out on our note sheet what the perfect squares are 1 through 15. Well, 1 squared, of course, is 1, right? 1 times 1 is 1. 2 times 2 is 4. 3 times 3 is 9, 4 squared is 16, 25, so on and so forth, right? You guys, at this point, know how to find your perfect squares, and we can fill in all of these up through 15. Right, so why is this useful? Well, the idea of simplifying a square root ultimately comes from taking a product that's already squared and essentially trying to figure out what the length of one side of that square was. So let's take a look at our notes and see if we can understand what we mean. When we first learned about multiplying numbers way back in elementary school, they showed us this box, right? The box method. Finding the area, multiplying a length times a width to get ourselves an area, right? And in this example, finding the square root of 16, really what that means is that the area of this box was 16. And so what was the side length that we multiplied together to make 16? Well, we happen to already have figured that out up top, right? We know that that side length is 4, right? 4 times 4, or this number multiplied by itself, gives us this area of 16, right? So the square root of 16 would be 4, right? If 36 is the area of this box, what do its two sides have to be? What times what? That's exactly the same thing gives me 36. Well, that, of course, would be 6. And so the square root of 36 is 6. But what about something like the square root of 20? If the area of this whole box is 20, well, what number times itself gives us 20? Well, you might be thinking, I don't think that exists. And to some degree, I can understand why you would say that, because there is no integer value that multiplies by itself to give us 20. And so the way we need to begin thinking about breaking down these square roots is to actually think about breaking down the box. Is there any sized perfect square that does exist as a factor of 20? Let's think about 20 and its factors. Well, what factors do we think of when we think of 20? Well, there's 1 and 20, of course. There's 2 and 10. And there's 4 and 5. Well, are any of these numbers perfect squares? Well, we have that right there, right? We do have 4 by 4 as an actual square, right? So we know that at the very least, inside this box, there's a box of 4. Well, how did we get 4? Of course, that is 2 by 2. But that leaves us with this uncomfortable L. And so there's got to be a way to represent this uncomfortable L without having to get into some really, really disgusting decimal. You may remember earlier on when we were talking about numbers way back in unit number 1, that we had an imperfect number under a square root. This led to what we called an irrational number, right? It could not be represented as a fraction. So how do we represent this ugly L as a way of other than a gross-looking decimal? Well, again, it's the idea of taking apart these perfect squares. Okay? What we want to do is take a look at our numbers and say, what is the largest perfect square factor that exists inside the number we're interested in? And we've discovered that it is 4. Well, one of the things that means then is that the square root of 20 is really the same thing as the square root of 4 times the square root of 5. Well, we can simplify the square root of 4. We know that that's 2, right? We just found that up here. And what's left over? Well, what's left over is this unsimplifiable number, the square root of 5. And oftentimes, this will be referred to as rad 5. Rad because the name of this symbol is a radicand. 5 because, well, that's a number, right? So 2, rad 5, is the simplest form of the square root of 20. Okay, and so we can see that, right? We broke out the perfect square that we knew, and we represented the rest with this radicand. So let's see if we can apply that same idea to some of these other problems. Does 54 on its own have a nice, clean, perfect square? Well, no, right? It does not. There is no number times itself that gets us to 54. We're going to just power right through the phone call that I'm receiving. Okay. What perfect square exists inside 54 as a factor? Well, let's think about factors of 54. Again, we're really interested in perfect square factors. So the simplest way to do this would be to look at the chart we just created at the top of our page and say, all right, well, let's think about perfect squares that are smaller than 54 and do any of those fit? Well, the next smallest perfect square from 54 would be 49, right? Well, 49 is not a factor here. The next would be 36. Is 36 a factor? No. What about 25? That doesn't seem to work either. 16? No, 16 doesn't seem to fit. And so we get to 9. Is 9 a factor of 54? And yes, we know that 54 is 9 times 6, right? So the square root of 54, or rad 54, is rad 9 times rad 6. Well, how do we simplify rad 9, right? Square root of 9 we know is 3. Square root of 6 is unsimplifiable. So the square root of 54 is equal to 3 rad 6. So what about 180? Well, some of us may not know off the top of our heads all of the nice factors, so we can again use this same strategy. Go up to the top. Is 169 a factor, right? And we can work our way all the way down. But that may feel tedious to some of us, and so it could be useful to figure out other ways to break this down. Right now, some of us may have been able to figure out right away, oh, I know that 180 is 36 times 5. And so the square root of 36 times the square root of 5 must give me the square root of 180, which means the square root of 36 is 6. The square root of 5 is no more simplifiable than that, and so we can get 6 square roots of 5, or 6 rad 5. However, not all of us may know this factor pair, but we may be able to use other factor pairs to help break this down. Okay? Again, being able to identify the largest perfect square is always going to be the easiest way to do it. But for some of us, we may have only been able to recognize that the square root of 180 possessed, let's say, 9, for example, right? 9 times 20 is 180. Well, that would give us 3 square roots of 20. But the question is 20 in its most simple form? The answer, of course, is no, right? We figured this out earlier, that the square root of 20 is the square root of 4 times the square root of 5, or 2 rad 5. Well, we already have this 3 out in front, right? So if 3 times the square root of 20 is 3 times 2 rad 5, well, what does that bring us back to? Right? 3 times 2 is 6, and there's our rad 5. So either of these methods will allow us to arrive back at the fully simplified version. What about the square root of 300? Well, the square root of 300, of course, is the square root of 100 times the square root of 3. And the square root of 100 is 10. 3 is as simple as it gets under the square root. We can also use larger numbers like this and context, right, to help us out. We know that the square root of 54, right, was 9 times 6. Well, that means that this must be 9 times the square root of 6 times the square root of 10, right? So we could certainly go that route, or 9 times 60. 3 square roots of 60. Does 60 possess any other perfect squares within it? Well, 60 is 4 times 15, right? And so 2 rad 15 times 3 would give us 6 rad 15. Additionally, we could have come to the conclusion that the square root of 36 times the square root of 15 got us to 540, and that's fine too, right? Either of those methods is perfectly fine. What about the square root of 10? Does 10 possess any perfect square factors? Well, the answer, of course, is no, right? 10 is just 1, 2, 5, and 10, and none of those on their own. I mean, 1, yes, but 1's not terribly useful to us in pulling out. So the square root of 10 is as simple as it gets, okay? Already fully simplified. What about the square root of negative 25? Well, when you get into Math 3, you will be able to unpack some different ways to think about this number. But as we look back at our square example that we started out looking at, is there any way for us to multiply this number times this number, right, and arrive at a negative area? Well, anything times itself will always yield a positive, right? Because you'll either have a positive times a positive, or you could, I guess, theoretically have a negative times a negative, but in either case, those would both end up as positive. And so the square root of a negative produces what we would call not a real number, or there is no real number. Okay? So that's reducing radicals. Now let's take a look at the back and see how we can work with these numbers. Combining radicals is very similar to combining like terms. Okay? Radicals will only go together if the radical matches. Okay? We could think of like radicals as we would like terms. For example, here you have 1 square root of 2 plus 3 square roots of 2. Well, if this was something like 1x plus 3x, we would feel perfectly fine combining our coefficients and leaving the variable in place, and the concept remains the same with radicals. If you have 1 rad 2 plus 3 rad 2, well, that's just going to be 1 plus 3 or 4, and then we leave the square root of 2 in place. We have 4 square roots of 2. If this was 5y minus 2y, we would be perfectly content saying 5 minus 2, 3y. Similarly, 5 square roots of 3 minus 2 square roots of 3 is 5 minus 2, or 3 square roots of 3. Now here's where these can differ a bit, right? Immediately we would look at this and say, well, the square root of 12 and the square root of 27, those are unlike radicals. But can we simplify these radicals? Does 12 possess a perfect square factor? What are the factors of 12 that are perfect squares? Well, 12 is the square root of 4 times the square root of 3, which would be 2 rad 3. Don't forget about this 2 out in front. That becomes 2 times 2, or 4 rad 3. Square root of 27, does that possess any perfect square factors? Well, 27 is 9 times 3, so the square root of 27 is the square root of 9 times the square root of 3, or 3 square roots of 3. So 4 square roots of 3 minus 3 square roots of 3, is this all of a sudden something that we can combine? In fact, it is, right? 4 minus 3, we're left with 1 square root of 3. That being said, if you have fully simplified radicals like we do here, 2 square roots of 5 plus 5 square roots of 2, that's essentially the same thing as 2a plus 5b, right? You can't combine that any farther. Therefore, this is as simple as it gets. Right? We've already had a little bit of a taste of multiplying, but just to see how this works, the square root of 3 times the square root of 2, this is the same thing as saying the square root of 3 times 2, which is just the square root of 6. Similarly here, just like we did with, multiplying variables with coefficients, we multiply coefficient with coefficient, we multiply radical with radical. So 6 times 4, 6 times 15, right? So the coefficients multiply out here, and the things inside the radical multiply here. 24, and then this would be 80. Now again, one thing we've got to be careful about is, can this be simplified anymore? Does 80 possess any perfect square factors? Well, we know for sure that 80 is 4 times 20. So that's one way we could think about this, right? 2 square roots of 20. 20 we know is 4 times 5. And so 2 times 2 rad 5, that is 4 rad 5, right? Now again, don't lose track of the original problem, because all of this, had a 24 out in front. 24 times 4 rad 5. This would fully simplify to 96 square roots of 5. What about division? Let's take a look at division here. Well, there's a couple ways that we can think about doing this. The first and the simplest way to do it is if you have like factors here, right? If we thought about 30 as the square root of 6 times the square root of 5. Excuse me. Right, there's 6 times 5 all over square root of 5. Well, we can simply cross reduce that square root of 5, and we know we're going to arrive at the square root of 6. If, however, we don't recognize like factors right away, there is a technique that we need to understand, which is called rationalizing, or to rationalize the denominator. Rationalizing the denominator means we're going to take this denominator and we're going to prevent it from being a radical number. Very popular on the phone today. Well, right now it's a radical. How do we take this and make it not a radical anymore? Well, most simply, we would need to square it, right? Well, the simplest way to square it would just be to multiply it by itself, right? If we multiply the square root of 5 times the square root of 5, we'll just end up with 5, right? Or the square root of 25, which could simplify to 5. We can then multiply the top by the square root of 5 also. But why would we do that? Why would we multiply the top by the square root of 5 also? Well, take a look at this number right here. What's going to be true about the square root of 5 divided by the square root of 5? What value does that number possess? Well, any number divided by itself, right? This has the value of 1. So ultimately, this goes back to a very old technique that we've learned with fractions so that we can change the representation of the number without changing the value, because all we're doing is multiplying by a value of 1. So let's see how that plays out. Okay, so we've got the square root of 30 over the square root of 5. And we're multiplying by the square root of 5 over the square root of 5. Well, 30 times 5 is 150. Square root of 5 times square root of 5 is square root of 25, right? Well, 150, that's the square root of 25, times the square root of 6, all over the square root of 25, and look at that right there. That all reduces down to the square root of 6. Exactly what we found at the beginning. Now, for one that maybe doesn't play quite as nice, we can use the same strategy. Multiply top and bottom by that value. Radical times radical, we end up with 7 square roots of 21 times 2, so that is 42, all over square root of 2 times the square root of 2 is just 2. Does 42 possess any perfect squares? 42 is 1 and 42, it's 2 and 21, it's 3 times 14, it's 6 times 7. Looks to me like no perfect squares exist. That's as simple as it gets. So go ahead and use these techniques to try out the Delta Math practice for tonight.